Actually, I have the book right here. It says, can read it? Devin, right? And the other hard copies, hard copies of anything, labs, promises. All right. 99 says the following. Okay, I was just talking about this one actually. A lob versus a bullet. So this is a quarterback either throwing like a nice short pass, a quick pass, or a lob over the top. So the only difference is what? That's the main difference you're going to notice. I mean, the speed might be different as well, but the angle is definitely different, right? So you have one more in the Y direction, one more in the X. This is actually right from the lab too, it's one of your questions. So the lob pass, A or B? B. Okay. It says the bullet pass is thrown with a launch angle of 25 degrees. What is the initial speed of this pass? So in part A, it had you find the angle of the lob pass. Now we're on the bullet pass, which means it's a lower angle. So the angle given is 25, so we can start with that. It says right off the bat, what is the initial speed? So we're looking for VI. It's going to be our question mark. Now, there's a figure here. The figure gives you the rest of the information. Did you notice that? The figure on the graph? Okay. So what would you call Y in this problem? What would you call Y in this problem? Well, you called 0. So let's discuss this, because this is one of the 4 categories of problems that you can have on this test. So the other day I was thinking about this, and I was like, well, you know what, you've got to break it into 4 main categories. And one of them is this, where you start and end at the same height, y equals 0. And whenever y equals 0, this problem becomes a little bit easier, because now I have a quadratic that doesn't involve a constant term. I could use y equals vit plus 1/2 at squared in the y direction, and I have 0 equals, which makes it really easy. I can just factor out a t, and a lot of you did this in your lab. You did actually a great job with this. So this is that kind of a problem. Now the x direction in the figure is given as 35 meters, so like a 40-yard pass. So we have these 2 values. We need vi. How are we going to get vi? What are we going to have to do for sure here? Because we don't have anything about time, right? We have no information there.
We're going to have to write this vi sine 25.
Yeah, so we're going to have to write our initial velocities in the x and y as components, but vi is not known. So when I write this, in the past I would use numbers. I have to write vi cos 25, and viy is vi sine 25. The reason I have to do this is because in order to solve this, I need linked equations, and I need those variables to show up in both spots. Because we're trying to find vi, it's just not known. It happens to be in both of these formulas. So it's in 2 spots already, which is actually useful for us. Because if we can get 2 other things, that are another variable that's in the same 2 spots, we can have a system of equations. So the automatic thing to look at is the x direction, because it's always easier. Right? I always start with the x direction. This is what we have. So we clearly need time as well. If we don't have time, we can't solve for vi, because vi is going to be embedded right here. So I can rewrite it, or I can just see that it's there. So I have to go to the y direction to get time, which is going to be my second variable that we're going to link together here. So in the y direction, I'm going to use this equation. And again, I'm using this because y is 0. VIY has VI in it, so that's good. We're still good with that. T is the other variable I didn't know over here, so that's good. At least it's the same variable. A we know is negative 9.81. So this equation allows me to come up with a system by filling in for the known. So 0 equals VI sine 25 t minus 4.905 t squared. And I can put parentheses around the VI sine 25 if I want to make sure that it's clear what's happening. But I don't really need to because it's all multiplication. All these are 3 different things being multiplied. Okay, sine 25, remind yourself, is one entity. It's a number. It's a value. You can't break up the sign in 25, so this is just 3 multipliers. Now we just solve for either t or vi and move it around. We want to get vi. So write this down as a little note to yourself. When you want to get one variable, solve for the other. It always works. Okay? So we're going to solve for t, is what I'm saying. So we want to get vi, so let's solve for t. So what will happen, in essence, is it'll get rid of t altogether, and we'll be left with just vi. So the goal is to get vi. Again, this is what we're trying to figure out. So let's solve for t. And I'm going to solve for t in the x direction, not in the y direction. Because here it's in two spots, I can't solve it generically for t. I can't just, I can factor t out, but then I know t equals something with t in the answer. It doesn't make sense. So I go to this side, because t I can get by just flip-flopping, right? I can switch these two here. And v bar x is right here, it's vi cos 25. That goes in there and just switch the whole things. So let's switch those entire pieces around. So on the left-hand side, this becomes time is equal to x over v bar x, which is really just x, which is 35, over vi cos theta. So this is the function for time right here. And that's going to go in place right over here and right over here. It's just a lot of algebra after that. It's messy algebra. You have to cancel stuff. Things reduce. Then you're going to have a vi squared term in a denominator. So you're going to have to get that by itself. There's an example we did in class, and it involves solving from this point on where everything cancels. I'll show the substitution, but it just takes a little while. So do you want me to continue on, or did you get to this point, or did you get stuck here? Where were you? You got to this point? Okay. So vi sine 25, substitution becomes 35 over vi cos 25. Remember, these are all numbers at this point. So if you'd like to, you could happily start plugging in values instead. This just makes it a little bit easier. And then it's going to be t squared. So what's going to happen is the vi is going to cancel here and here. Sine 25 times 35 over cos 25 is a number. Let's put a number in this place then, right? So let's cancel the vi's right away, and then put a number there for what's left over. Vi and vi cancel. Remember, this sine 25 is really over 1, in case for those of you that aren't seeing the cancellation. This vi sine 25 is over 1. Cancel here. Multiply these two. But you got to do sine 25. Some of you are still doing this. Some of you are doing 25 times 35 and taking the sine of that. This is the sine of 25. Do that first, multiply that by 35, or just put 35 in front on your calculator. Okay? Get a value for that, and then on the right-hand side, here's what we're going to have now. We're going to have minus the 4.905 times 35 squared over vi squared cosine 25 squared. And in math, you're going to write that a different way, but because you haven't seen it the new way, I'm not going to get into it right now. Right, the square actually goes in here. It says cosine squared theta, but for now, I'm going to leave it outside. So remember to square these three terms. Take a look here, please, if you haven't seen this. Okay, all three of these have to be squared, because this is really just a simple product. These are multiplying each other, right? And this is division, and division is defined as multiplication by the reciprocal. So this is all multiplication. And whenever you have that situation where everything's being multiplied, and it's squared or cubed or whatever, every term gets squared or cubed or whatever. So I have to square all of those three values. Another common mistake in algebra here. So although I said it's just algebra, it is a little bit tricky, but you just got to do a little bit of practice with it. Anybody get a number for that first piece there? What do you got, James? 16.3. So at this point in time, I would probably move this whole thing over. You can get a number for these guys right here. Leave vi squared alone where it is in the denominator. Get a number for the product of these divided by this number. That number all goes up top. Leave the vi squared in the bottom. Move the whole thing over. Switch the vi squared and 16.3 in that direction and solve. Anybody got it for me or have the next number? I'll have you write it down, but just give me numbers. Go ahead.
The numbers for the numerator is 6,008. And then I got vi squared cos 25 over that. So then I divided it to the other side. I got 14.79 equals 6,008 over vi squared.
You divided it to the other side or added it?
The cos 20. If I divided it.
So what goes in the denominator under 6,008, James?
Vi squared cos 25.
Cos 25 squared?
Yeah.
The whole thing? So what I'm saying is do this. Make it even easier. Find out what this number is as a whole. And that number can just go in the numerator. Because think about this, right? If vi squared is by itself in the denominator, just divide these two things real quick and get one number in the numerator. So it's one number over vi squared. It really doesn't matter. I'm just saying if you're going to do all the work to simplify a number.
Is the
about 7,315.2 pounds.
Okay. Over VI squared. Now, since this is 16.3, what I can really do is I can move this entire thing over, and it becomes equals positive 16.3, and then just switch those two. So this seems messy, I know it, because it's a lot of work, but it is literally all algebra at this point. So VI is the square root of this. And it would be plus or minus, but we're throwing a lob pass. We're finding the overall initial velocity. We're not looking at positive y or negative x or anything like that. So although it's positive or negative, you are going to take the positive root of this answer. So whatever that turns out to be. So this is one of 4 types of questions. And this type of question involves a y value that is 0. Okay, that's one of the big standard ones we're going to see. What are the other types of questions? I'm going to scroll down a little bit so you can keep writing. I want to start jotting these 4 things down. So when y equals 0, we could draw a figure of that, right? Starting, ending, on the ground level. The initial velocity is given in these kinds of problems or being sought after, and then theta would be given or sought after if not. So that's the first thing. What are the other types of problems for projectiles? Okay, we'll start and end on the ground. Go from there. Go ahead.
So you start from like a little bit of a y to get a lower one?
Yeah, well, you start at a different height that you end at, pretty much. Either you could start 2 options. Which way? Above or below. So everybody, just take a look at my hands real quick. You're starting here, ending here. The objective is to go at the same altitude or have a 0 altitude here. So if you start up here, you're going to have a negative y. You start down here, you have a positive y. What does it do to everything? What's the difference in the second type of problem now? God bless you. How do you solve the second type of problem? What do you have to use? Come on, pick up on this by now. If you have a constant now, go back in your mind. You got to start to visualize this stuff. Look back at the equation up here. Let's take a look at this part right here. Now imagine we have a y value. We have to put a number here. So what is the difference here that we end up getting? How are we going to solve this if we have a number there? N. In this case, VIY has a value because it's launched at an angle. You're thinking of the horizontal fired one. When it's launched horizontally, it is. But still launching at an angle. I'm just saying, what's the difference when we have a number here suddenly when we didn't have a number? So if I normally have this problem and I have 0 equals, let's say the VI was 25 t minus 4.905 t squared. Why is that so much different than if I have a number on the left-hand side? Joe?
Because you're trying to make the other side equal 0, and then when you have a...
Okay, so how would I go about solving this? You all did it in your lab, so I'm not getting why we're not answering this quickly. In the lab, this was a problem. Literally, different VI, literally that problem. How did you go about solving this? Oh. Thank you. You factored out t. And 95% of people factored out t, so I don't know why I'm getting a stared look right now, an empty look. You should know how to do this. I saw it done in your lab. 0 equals t, parentheses, 25 minus 4.905 t. Set each factor equal to 0 by making a t chart. 25 minus 4.905 t equals 0. And then solve. This will become t equals around 5 seconds. So this would give me the 2 answers for time. So why is this second type of question more difficult than when I have a number here? Can we answer this question now, please? John?
I just have a question about what you just did.
Okay.
Why is it, like, could you just go through the entire thing again? Like, I just kind of like...
What thing, Joe? On the top right?
Where like t is equal to 0.
Yeah, so remember when you factor things? And if you factor, got to go back to math. Look in the bottom left over here. Let's say we've got x squared plus 4x plus 3 equals 0. This factors x plus 3, x plus 1. Agreed?
Yeah.
What do the answers become, Joe? When you solve this afterward, remember how you have to solve this? What do your answers become for the x-intercepts or the roots?
So make it equal to 0, so it would be -3 and -1.
And you did that by making it equal to 0, you said, right?
Yeah.
So that's the exact same thing we're doing.
Oh, okay.
See what I'm saying?
Yeah.
I just don't show this step usually in math and just say x equals -3, x equals -1. It's the exact same thing. Set it equal to 0 as a factor. The zero product property tells me in math that anything times something equaling 0 means that either of these could be 0. It could be 0 times 5 or 5 times 0. So either could be 0, so you try and both equal to 0 and solve them both. Why is this answer not giving me any information? T equals 0. I've discussed this with several individually. T equals 0. Why does that have no significance, or why does that have no help in the problem? It does solidify something that this answer is kind of right.
Because you're given what it is when time equals 0.
At time equals 0, what is it, James?
0.
Yeah, where is it physically? Where is it? It hasn't moved. So remember, this question, go back real quick, is saying when is the height equal to 0? You plug a 0 in for height right here, which is at the beginning and then at the end, right? So at what times is the height equal to 0? At the beginning, t equals 0, it's at 0 height. And at the end, t equals 5 seconds, it's at 0 height. So in these kinds of problems, you have to recognize that these two answers are not redundant, and this is just before the problem even started. And this is the answer you're getting. So to answer the question, if we get a number now, though, here instead, or giving me a number right here, please, can I do this? Am I allowed to simply factor out a t if I have a number over here now? Am I allowed? Please answer the question. No, I'm not. So this number moves over, right? And how do I then have to solve this is what I'm asking you.
Quadratic.
Thank you. Some sort of quadratic formula. The formula itself, the program itself, or graph it in y1 and find the x-intercepts. Any of those methods give you the time. But remember, when you have a number in this spot, the problem becomes a little bit more difficult because you have to use a quadratic formula. If this is a 0, you could just factor out the t like we did and solve this problem like so. So that's the second type of problem I've been looking at. It's also the second type because it's different. You're starting up or down. So you have to recognize that instead of y equaling 0, y is going to equal plus or minus whatever the height change is. So I think about this problem as option A. You're starting up here and you're ending down here. Or option B, you're starting down here and you're ending up here. So what am I doing right now? I'm trying to get you guys to kind of summarize what we're doing before 4, right? That's why I said there's 4 categories of questions. Here's 2 of them. I might have used these as one separately because I'm thinking of the third. I can't think of the fourth. What's the third type of question that we've gotten into now? We've done another type of question actually, and I think Anne mentioned it already. Anne touched upon this type of question. And what did you say VIY was equal to in one of these problems?
0.
Yeah, what kind of problem was that? Anyone remember when VIY is 0? This was a specific type of question. VIY is 0 means all the V is in the what direction? If the VIY is 0, all the V is in what direction? In the x direction. So if all the V is in the x direction, what kind of a problem is that? Chris?
It's like where it translates at constant horizontal velocity.
Yeah, it starts, we should say, at a constant horizontal velocity, and it does end up going down, always. Very good. So it starts at a height also, these problems, and it's launched horizontally, and it's the half parabola problem where it has to come back down. So it's similar to problem type 2a. Look at problem 2a. 2a looks just like this, but what's the difference in 2a and then problem type 3 here? James?
A has a y and x among those.
Very good. A has a y and x does not, and 3 does not here. So look at the blue vector I drew, and as James said, that's what he's referring to. A has a y velocity. It's got an x and a y velocity. That's the triangle we have here. This has only x velocity to start. Why does this problem become very easy? Because in problem type 3, when I said VIY equal to 0, I can do a lot, right? That takes off the VIYT term in the equation y equals. Remember, this is the equation that you use. So it drops off this entire term. That's the key here for this problem. Again, even in the first type, you're still going to use the same equation. I could jot that down and just write this down and say y equals VIYT plus 1/2 AT squared. And this goes to 0 in this equation. Right? Y is 0 there. So that drops off here, and this drops off. I just remembered the fourth type. What's the fourth type of question? It doesn't involve the full flight. I'll give you that.
Is it when you have 5 max height?
Yeah, the max height problem. The max height problem. So the max height problem could involve either doing what? Having a symmetric path or an asymmetric path. What do I mean by that? Symmetric versus asymmetric for a path here. This is the fourth type of problem. What do you see with symmetry or not here with the max height problem? Why does symmetry come in hand, I should say also? What are some things I would know? Chris, what do you think? Yeah, so that's the huge part that Chris just pointed out right there. Time up equals time down when it's symmetric. So we get up a max height problem when it starts at the ground and ends on the ground, and that's where time is equal on both sides. So if you got the total time, what would you do to get the time to max height? Take half of that time, plug that time into the y equation to find the y max, the maximum height itself. So let's talk about the two types of max height problems here. Let me just put a little guy here so we can see. This is part A first, when it starts and ends on the ground, or at the same height, I should say. When this is the case, we could say that time to max is equal to 1/2 of the time total. If that doesn't make sense to you, write it in words, but this makes sense to me if I write it later. The time it takes to get to max height is equal to the total time itself, times 1/2, or divided by 2, whichever way you want to think. So if I want to find y max in this problem, I could find y max by going ahead and plugging in t max. I can use VIY times 1/2 t total. So half of the total time I can plug in here. And I can plug it in here also. Let me zoom in on this a little bit so you can see it better. So this is what I would think about. And a couple of you did this in the lab. This was great. I actually didn't even use this method in my solution. So this was an alternate way to do it. To find the time to max, just find half the total and plug it in. And that's actually probably the easier way. I used VF squared. So let's take a look at that second type of problem now for max height. So problem type B for max height is going to be when you don't have symmetry in the problem, or you don't know the total time, maybe for some reason you want to start doing it a different way. But I like to think of this as not an asymmetric problem. So let's start up or down. It doesn't matter. So for this problem, we have to consider, if I want the max height, it's not going to be halfway through, so I can't use half the time. So that method is gone, right? So if I'm trying to find max height, what do I know about at this location? What do I know about velocity here? I know something about velocity at max height. Give me something in. What part is 0 in? You can't just say the whole thing then. I need you to be more specific, right? If you're on Jeopardy right now, Alex would say, be more specific, please. What part is 0? Think about it. It stops going up, right? And up and down is what direction? So which part is 0? So the velocity in the y direction here is 0. Remembering, though, that the x component is always constant. There's always an x component of velocity. So what I can do is I can split the problem up from beginning to end. Make this the initial starting point, and make this the final. And forget about the rest of the problem. So this is the method we approach and take in these problems. Where you remember I said truncate it or cut it into pieces? And we did this in the last chapter also, where we threw an object up. You can think of the first half as the way up, and the second half as the way down. Well here, let's only take a look at the way up, because all I care about is the max height, and at the end of the way up, you're at max height. So as a result, we call that the final location, and we could use two equations. We could use this, to get the max height, and that's called y max, so I'll call that y max. Some of you have been doing this, which is great. I like that idea of putting a subscript here. So VFY is 0, so that's why this equation becomes very useful to me. Tell me my pencil stopped working. Of course, it just died. So let's cross off VFY, that goes to 0 here. What's the second equation that we can use? What's the second equation that allows us to find something besides y max? This is y max that we'll solve for. If we have the initial velocity, we have acceleration, it's always the same. This is 0, cross it off, please. What's the second equation? Come on, people. We're using the final velocity here, so what's the other equation we have not touched upon at all today? Same hands. Sophie, go ahead.
VF is equal to VI
Good. Vf equals Vi plus At. And I'm gonna point in the y direction, so I'm gonna write this all in the y direction. And again, these VFs both drop off. That's the key for these problems. That's what makes life very easy to solve these problems by using this method. So these are really our 4 types of problems that we could consider for projectile motion. Okay, those would be like the 4 things you really need to know when it comes to problem solving. How about some other key facts? We need some other things. What are some things you also discovered? Let's run off some key facts. Maybe we'll put those in like the bottom left corner over here. What are some facts? What are some things you discovered throughout the chapter? Come on, I know you know things. You wrote them in your lab. Participate. Let's go. What are some facts? What do you think? I appreciate it, but for now, I need other people to help out. Come on, what's a fact? Guys, this is not hard. You wrote a million things in your labs. You have your notes to look at all the time. What angle is the optimal angle? Chris, thank you. 45 degrees gives you max range. I agree. Second fact. Come on. What else? Yes?
30 and 60 degrees, even though 60 has more hanging time, but they're going to land in the same place.
Very good. So complementary angles, is how we would say this. Complementary angles have equal ranges. Equal ranges. So not just 30 and 60, Andre, but that's a good example. So 80 and 10, 70 and 20. So complementary angles have the same range. So if we could say x1 plus x2 is equal to 90 degrees, then the range for x1 is equal to the range for x2. I'm just using shorthand as how I would write it. How about a third fact? Yeah.
If the angle isn't below 45, then there's more x velocity.
Good. And then?
If it's over 45, that's more y velocity.
That's the first one, and then here's the second one. You would literally just write the opposite. Okay, absolutely. These are great facts. What else? We already stated a couple others, right? The time to max is half the total time if it's symmetric. What else? Yeah, Chris, good.
The more y velocity, the longer the hang time.
Yeah. As theta increases, the total time increases. So does the y displacement, right? All those things increase altogether. We saw that in the lab. There's one other thing about it's different. Yeah, go ahead.
Velocity.
The more x, the less hang time. Yeah, that would be the opposite of that. I agree. Absolutely. As theta goes down, instead, more x velocity, you get less time, so you can draw them indirectly. There was something else, though, about your horizontal range. Up till 45, as theta increases, what happens to the range? So theta equals 0, the ball doesn't go anywhere. Theta equals 1 degree, little bump. 2 degrees, bigger. Up till 45, it goes as far as possible. And then after 45, what starts to happen to the x component of the displacement, right? It decreases. Very good, the range. So from theta equals 0 to 45, the range increases, but as theta increases from 45 to 90, the range decreases. These are great facts. So this is literally like a list of things that you've kind of discovered. This is where you could expect multiple choice problems to come from, right? The formation of the problem stems from these concepts. Anything else I'm not thinking of that you could think of?
I was going to say that x velocity is always constant.
Good. X velocity is always constant. That's something we have to write down because A is equal to 0 in the x direction because of no air resistance. So therefore, V bar x is equal to a constant. Anything else? That's A in the x, by the way. It's saying like acceleration in the x direction. How about other types of problems from the problem set? Or anything from 5.1 you want to ask also? Because you did have to watch, like, remember the third law for every action is an equal and opposite reaction? Okay, you know, we can start a little on the concept of it. Did you understand the idea of how equinox reactions don't always prove to be the same result with the Earth? Right? When I jump, literally, I'm pulling on the Earth with a given force. The Earth is pulling on me with the same force. Yet, how come I get pulled down to the Earth and the Earth doesn't get pulled up to me?
The Earth's mass is so.
Earth's mass is proportionally so much greater than mine that the Earth's acceleration, although the Earth does move, so it's kind of weird. There's always been the question posed, and is actually anybody watch or look at the channel Vsauce? Vsauce on Sun? There's a question. It's a really cool question. If everybody on the same side of the Earth jumped at the same time, what would happen? Because think about it, right? When you jump, you're literally pulling the Earth up to you, and the Earth is pulling you down to it. But because the Earth is so much more massive, it doesn't really move. Its acceleration is with like a million zeros and then a one. Technically, God bless you, is some acceleration because you're providing a net force from the Earth. By moving away from it, you're causing you and the Earth to want to pull together. So if everybody did it at once, could it be enough force to like tug the Earth up to where the people are instead of people back to the Earth? If you're curious about it, check out that channel. There's an answer to it. There's a whole lot. There's a whole reason why. What else? Anything else for this? I'm trying to think. What other questions do you want to go over? There were a slew of math problems. I gave like sample math problems with solutions, about 9 of them. That's something that's useful to look at under documents and handouts for practicing for the test as far as mathematical difficulty. You could expect them to be kind of like those. These are the main 4. You could probably expect at least 3 of the main 4 questions to be on there. 4 questions, 5 questions. Where are we at? You have a lot of terminology. Want to make a terminology list real quick? I think that'd be something that would be useful for this kind of a test. The words that you definitely need to know. So let's see. Inertia, net force, projectile/projectile motion. Your key terms are like T max and Y max. These are new. Those just mean the time to max height and the actual max height itself. Generally the word force, so net force or just force itself. I looked at my notes to find keywords. That's why I'm looking for you now. We should recognize this word, component. I use it a lot, so it might show up somewhere. So if we're talking about the horizontal component of the velocity or the vertical component of the velocity, stuff like that. We drew a conclusion from an interesting type of problem we've discussed here. The concept of firing something horizontally and it falling to the ground. And then the whole same thing of imagine the same object is dropped straight down. And it falls to the ground. What conclusion do we draw from that? What conclusion? Chris, yeah. They have the same y velocity, very good. Which leads me to what conclusion now?
That the x and y velocities are really high.
Okay, keep going though. I need a general conclusion. You're right. The y velocities are both 0. It's like a free fall in both cases. One is dropped and one is launched horizontally. What could I say about the resulting time it lands? Time should be the same. That was a concept we demonstrated with that little tiny launcher that launched one at the same time it dropped the marble and it hit the floor at the same time. The whole concept is that a horizontally fired projectile can be treated as a free fall in the y direction. That's why whenever we do this problem, when we do our x and y direction, like we showed earlier, in the y we always do VIY equals 0 because it's pretty much the same problem. We talked about air resistance a lot. You could expect problems with air resistance, discussing what air resistance is, what could be factors that affect it, the resulting motion of an object with or without air resistance, comparing the two. What does it really do in whole? How could you summarize that? A lot of you did a good job in your lab. What's the whole concept behind air resistance? What does it do?
It slows down the object so the range is shorter than what it would normally be.
Yeah, most of its parameters, y max, time, and range were all shorter than they would be with air resistance on. Again, we're assuming it's always resistance. I think, Rodrigo, you pointed out that you could have tailwinds that help you, and that's true. And like planes, they do fly with the jet stream at times, so the tailwind actually pushes the plane. It's not a resisting force, it's almost an accelerating force, it turns out. That's why you could fly faster sometimes and make up time. But we're going to assume that it's a resistive force. Okay, I've talked about what it's a function of several things, mainly its parameters, the shape, the actual contact area, the surface area between the actual fluid, the fluid it's passing through. So we've talked about, remember, I think somebody asked about a bullet fired in the water versus fired in the air. Is that why it slows down? Because the resistance, it's a fluid resistance. Air is a fluid. Liquid underwater is a fluid. So your hand going through the air is the same as a bullet going through water, except with a lot more resistance because of the properties of the fluid. So the fluid matters, the surface area matters, and how fast it's going matters. Those are the three real characteristics that affect air resistance that are gonna change the resulting motion of a projectile. What's up? Yeah. What does inertia tell me? We've talked about inertia. I'm going to definitely talk about it. It's going to be on your test. I spent a little bit of time on it. What's the whole idea behind this concept? Why is it applicable? Why does it matter? We haven't gotten into heavy math with this yet, I know that, but just based on what we've talked about already. What does it state? The law of inertia, the first Newton's law. What does it actually state?
Is it an object at rest stays at rest? The object at rest stays.
Yeah. So if you're doing something, you're going to remain there pretty much. If you're moving, you're going to keep moving. If you're not, you're not. Unless acted upon by some other force. And that's the whole key. That's the whole caveat we have to consider. So imagine a football player running down the field. He's not going to be stopped until what? Another force attempts to stop him. Or her. There are professional women's football leagues too. Actually, I see how today. So, I mean, in the sense of constant motion here, if you're moving, you're going to keep moving. Unless some sort of resistive force attempts to stop you, whether that be friction or another object. Yeah.
It was a problem on the
Problem set?
problem set that was kind of like this. I think it was an astronaut and he had a jetpack on or something. He was in space and he didn't have enough fuel to get back to the spaceship. So the reason why he could get back was because he could push off and then he would go back to the
Yeah, that was on your problem set?
I think so, yeah.
Okay. He had his backpack with him and he was stranded kind of in space, right? So a lot of that goes to actually more of momentum. I'm not interested in why I put in the problem set. There's probably a reason. But the concept is that if you were to throw something, the actual momentum of that object will be equal and opposite of yours, which would push you back. It's actually Newton's third law it comes from. Every action is an equal and opposite reaction. So by you pushing the bag, technically the bag is also pushing you back. So that would be your way to get back to the space station if you're stranded. It's like reverse thrusters. That's what you think of, right? If you wanted to land on a planet, as you're coming down, you put reverse thrusters on to steady yourself. Same idea. Good question. James?
Will we have to do one of these problems where it's like the in 5-1 the velocity changes over a period of time?
So if you're trying to find the overall force acting on a body?
Like a car braking, then you use that to do something.
Absolutely. So an example like this James is asking about, so imagine a car is going with a velocity of 25 meters per second and slows down to 4 meters per second in a time period of 4 seconds. And the mass of the car given in this problem happens to be, I don't know, what's a reasonable mass? Because it's times 2.2. So let's say 1,000 kilograms. It's about 2,000 pounds, about a ton, decent sized car. So it's starting at a velocity of 25. Let's label that VI. It's ending at a velocity of 4. It's braking. So we're trying to figure out what is the braking force being applied. Force equals mass times acceleration. I've got mass, but I don't have acceleration. So I have to go back to kinematics. These are the kind of problems you could definitely expect where you use old school stuff. How do I find acceleration? Acceleration equals? A equals? Chris, go ahead. Yeah, V over T. Delta V over T. And that's going to be final minus initial over time. And we've got those values. 4 minus 25 over 4. Okay, VF minus VI comes from the givens in the problem. This was the speed of the car initially. It slowed down to this velocity in that much time. Plug goes in, you get an acceleration. Why is the acceleration negative? Why is it negative? You're slowing down. Okay, you had a positive velocity. The only way to slow down is with a negative acceleration. Remember that from that table. That's from a while back. So this is negative what? 19 over 4? Or negative 21 over 4? So whatever that value turns out to be. Negative 5.25. Units of meters per second squared because everything was given in standard units. We can assume that that works. Meters per second and seconds. I plug that value in, multiply it by my mass to get the overall force. Okay, so just move it 3 zeros. And that'll be a negative value. Trying to think of other types. We have a couple minutes still. It's an A day today. Other types. We haven't gone through a minute and a half. We talked a lot about the velocity changing on the way up and down and having those vector diagrams. That's a good diagram to know. Like the initial velocities in both directions. Then it gets less in the y, less in the y, less in the y until at the top it's only in the x. Then it's in the negative y, more negative y, more negative y as it goes down. Yeah, Andy? Yeah.
Or you have to know how to figure out the distance traveled after you break.
Hypothetically, should you know how to do that? Hypothetically, sure. Because you have acceleration, right? And this kind of problem is right here, is your acceleration. Take that value, use x equals VIT plus 1 half AT squared. You've got VI, you've got time, you've got acceleration, you can find x. So hypothetically, yes, you should be able to do it. Is it going to show up? Probably not. Okay, but that kind of a skill is something you should know because on the midterm guaranteed, you have to put all these together. Like you have problems that are all connected to each other. So you'll see you got a kinematics connected to a projectile, connected to force. Anything else I want to mention? Please study hard tonight, okay? If there's anything you could do, it would be to do the 9 sample practice problems. You still have a lab due tomorrow, okay? You have homework 5-1 due tomorrow. There's a lot of stuff going on, so please make sure you spend your time wisely. I will be here after school today if you need somewhere to work or you want to ask more questions, okay? Check my schedule. If I do, come on. My website is right here. If not, just get on the email. First page is all the questions and the answers. And the next page is, yeah. After that, so do it. Don't look for solutions. Trust me. We're going to want to solutions. Like, oh, yeah. But anyone wants to do it all. Yeah. Try it yourself.
Can I get my lab?
Thanks, Chris. Yes. I think you're right on top, actually. Do you have work for me?
I put it on Google Drive.
Awesome.
Wait, only Mark has to submit the report for the...
As long as one of the two of you do.
Okay.
And you put both names on the...
Yeah, you got it.
Do you see Sophie at all?
Daniels?
Yeah, throughout the day. She just left, I know.
Yeah.
She never got a lab.
I think I passed it right now.
Do you mind?
Yeah, sure.
Give her a lab?
Yeah.
Thanks, Chris. How are you? Watching any game last night, Steve?
Nah, I didn't very much. I watched, on and off, my dad was watching it, but...
I wasn't sure. Oh, who's coming in here? Who teaches? Does he use the overhead? Huh?
I cut off after it was 4-0.
Yeah. Turned out to be crazy. I never would have believed it.